So do you see that if every point on the line has an x-coordinate of 7, that can't be parallel to the x-axis? Can you imagine that? Yeah, so if every point on the line has an x-coordinate of 7, then that line basically lies in the plane x equals 7. So it's some kind of line. So it could be like this, or it's like this. It could be up here, but that line can't be parallel to the x-axis because it's in a plane that's perpendicular to the x-axis. Okay, so that's got to be false. This one, y equals ln of x means that x equals e to the y. And so then you could say y equals t, and then x would be e to the t. So that's actually like a Calc 2 problem, but we're reviewing that. So this is good, it works. And then finally this one, maybe this was the tricky one. So yes, the t's are squared, but if you look at what's going on here, you have x equals this thing, and then y equals 5 times that thing minus 9. So if you were to eliminate t, it would be y equals 5x minus 9. Because x is this. This is x right there. So t is doing weird things with in terms of how this expression is doing weird things to t, I should say. But in the end, the points that you get are 5x minus 9. You don't get them in a nice linear fashion. You know, for different values of t, it'll sweep out at different rates. But in the end, you're getting these same points on the line. So it's true, that is a line segment. Any questions on that? The rest of the homework you had pretty good success on. So let's keep working on like surfaces and vector functions. Okay, let's start with this one. So first of all, can you sketch these surfaces right here? Z equals square root of x squared plus y squared, and z equals 1 plus y. Could you sketch those and maybe sketch the intersection of those? So I'll say, is it a sphere? Because if you square both sides, you get z squared equals x squared plus y squared. Gavin likes it. Is it a sphere? So with a sphere, all 3 of your terms have to be positive on the same side, right? Because it'd be like x squared plus y squared plus z squared equals something. So this doesn't work out because you got it. This z squared would like to be minus z squared. So remember what this is?
Circular, like paraboloid.
Okay, almost. Paraboloid is, remember when this one is linear, and we talked about last time. This is the cone, right? So this is our double cone. So then if you take the square root, you get what? Just the top half. Because or you take the square root, you get plus or minus. So positive z's would be the top, negative z's would be the bottom. So if we just have the positive square root, so it's a cone. Right, lateral sides it goes up in a linear fashion, right? In linear fashion, because in essence, the radius of the circle is the z coordinate. So the radii and the z move up together, so you get a cone because you get a constantly increasing radius with z, right? Constantly increasing radius with z. Okay, what about this one? David, how about this one? Yeah, it's a plane. So it's like, or like a cylindrical line, right? You could just draw the line in x equals 0 and imagine all x values, and then that just makes a plane. Okay, so now, what about the curve of intersection of those two? So our goal is, so those are going to intersect in a curve, and we want to write the vector function for the curve, right? So when surfaces intersect, they intersect in strings of points. And we know that strings of points are represented by vector functions that you worked on in your homework and we did Monday. So what would be this intersection of these two? Okay, and why do you think it's a parabola? Okay, so he's remembering his conic sections. If you cut cones at different angles, you get these different curves. And so what is it that makes this one a parabola? So what's special about this plane relative to this cone? Do you see? It's parallel to the edge, right? So this particular plane is just perfectly parallel to the edge of the cone. And so yes, it does cut in a parabola. So I can show you that here. Show up? Yeah, so that yellow curve is showing us the curve intersection of the cone and the plane. So our goal now is to write the vector function for that, and so we're expecting it to be a parabola, and it should turn out that way when we do the math here. So we've seen there's kind of two major strategies to writing these vector functions. One is that you would let one of your variables be t, and then figure out what the others are in terms of that. What's the other strategy for writing vector functions? You saw them in your homework. What's the other common way that we saw vector functions, where one wasn't necessarily t?
Sub 1 in or something?
What's that?
Kind of sub 1 in.
Sub 1 in. Oh, that, yeah, so we'll always do that. Did you see any cosines and sines in your homework? Is there any cosines and sines? Yeah. And what's that about? Why do we use cosine and sine? Circles and ellipses. Circles and ellipses are modeled with cosine and sine. So if that is a new idea, it shouldn't be, but if it's a new idea, then make sure you remember. Circles and ellipses we model with cosine and sine, because by definition, cosine is a horizontal coordinate in a circle, and by definition, sine is a vertical coordinate in a circle, right? That's what cosine and sine are. So by choosing two variables to be cosine and sine, you get a circle or ellipse in the plane of those two variables. Okay, so will we use cosine and sine for this one? No, because it's a parabola, right? It's not a circle or ellipse. We know we're expecting a parabola here, because the angle of that plane is the same as the angle of the edge of the cone. So because we're expecting a parabola, we're not going to do this using cosine and sine. So we need to we're going to bring these two equations together and we need to write the vector function for the intersection. So our x, y, and z, whatever we choose for these functions for x, y, and z as a function of t, have to be consistent with both surfaces. If they're consistent with both surfaces, then we're defining the points that lie on both surfaces, or the intersection. So, what should we do?
Substitute y for t.
He wants to set y to t. What do you think about that? If we set y equal to t, then what could we get? Z very quickly. And then could we get x from that? How would we get x? Well, we'd have this equation, and we'd have to figure out what x is. Substitute in our z and our y with t's, and figure out what the x is. So y, I think this is a good strategy. Y equals t. Yeah, this goes down. Okay. All right, so y equals t, and then so what would z be? Piece of cake, 1 plus t. All right, well now our work begins. How are we going to get x then? So we got t 1 plus t. And so, what do we got? It'd be 1 plus t equals square root of x squared plus t squared. And now we got to do the math, right? We got to do the math, figure out what is x. So we're going to have, how we do that, we're going to have to square both sides. We're going to have 1 plus 2t plus t squared equals x squared plus t squared. So x is square root of, is that right? Yeah. So what happens here is, if we want to write that whole parabola and we're using y equals t, this is going to take two different vector functions, right? And so that's kind of not good. So it's correct, but it would take two different vector functions: a vector function for the front half where x is positive, and a vector function for the back half where x is negative. So it's okay. That's kind of how math is sometimes. You try something and see where it leads you. So that wasn't a totally wasted exercise. We see the general gist of it. But if we want to avoid this, what might be another way to start this? Z equals t. Yeah, I think maybe x equals t. Maybe let's try x equals t. And then we know that z is 1 plus y, so we can figure out what y is, and then z will be easy. So let's try it. So try that. So why don't you try that? Start with x equals t. And then you'll have what? 1 plus y equals square root of t squared plus y squared. And see where that leads us. Is it better? Does it work? Do we have that plus or minus situation? Don't this time. So this is more desirable parameterization. That's better. Because now one function gets us the whole parabola. See that? Any questions on that? All right, so now what if it was the plane z equals 1 plus 1/3 y? Or 1/2, let's do 1/2. Z equals 1 plus 1/2 y. What would be different? Yeah, Paul?
It'd be an ellipse.
Okay, why?
Did you say why?
Yeah.
Because the plane has less of a slope in y direction, so it comes and cuts off.
Okay, so it's going to be like angled more shallow, right? It's going to have a more shallow angle than this one. And so then, turn this off. I'll do 1 plus 1/2 y. This is a new problem now, right? This is a different problem. Change the plane. So how are we going to do the same thing? X equals t for this one. The intersection is an ellipse. An ellipse in which two coordinates? X and Y, right? So it's an ellipse in X and Y. Does that show up? Let's start. So it's an ellipse in X and Y. So therefore, what could we do? Yeah, we want to use sine and cosine for X and Y. Yeah.
Would you do that like R equals cosine things?
What do you mean?
I remember like X equals R cosine or X equals R cosine.
Right. So X and Y are going to be functions of cosine. So X is going to be something with cosines in it, and Y is going to be something with cosines in it. But what needs to happen is, when we do that, so when you do this, it's all based on the fact that what? Cosine squared of an angle plus sine squared of an angle equals, so when you parameterize with cosine and sine, this has to be true with the relationships of your surfaces. So I'm not just going to say x equals cosine t and y equals sine t and solve for z, because that might not keep this relationship true. This has to be true as well as your surfaces when you parameterize in cosine. So what we're going to do instead is we're going to figure out what ellipse we have. So that to get the ellipse we have in x and y, we eliminate z. So we have 1 plus 1/2 y equals square root of x squared plus y squared. And that's an ellipse. So, and that's going to be the ellipse that we see when you eliminate z, or you look down and you project it into the xy plane. So we're trying to find the equation of that ellipse. And once we have the equation of that ellipse, then finding the z part is easy, because just 1 plus 1/2 whatever the y was, right? So how do we get that ellipse? Well, we have to do the math, right? Do the math. So it's kind of like we're trying to get this into the equation of a circle, but we know it's going to be an ellipse instead of a circle. But those are very similar equations. So we're going to start again as before, square both sides. So okay. And then we're going to gather up everything that doesn't have that has an x and y over here. So let's move everything to the right here. So it's going to be x squared plus 3/4 y squared minus y equals 1. Did I do the math right? Is that right? So remember, what do we have to do? Remember, we did this with spheres, but actually we have to. So let's get rid of this coefficient of 3/4 on the y squared. So let's multiply by 4/3, because the x squared is fine, and we'll have y squared minus 4/3 y equals 4/3. Remember what we had to do to get the equation of a sphere? When it was something like this? Complete the square, right? We got to complete the square on y, which is half of that squared. Half of the linear coefficient squared, which is what? 4/9. Half is 2/3, squared is 4/9. Add that to both sides. This is 12/9, 16/9. Check my math. I think this is 12/9 plus 4/9 is 16/9. Okay, so now we've got it. 4/3 x squared plus y minus 2/3 quantity squared equals 4/3 squared. Now for an ellipse, so again, we're working towards, we need to figure out what our x and y is in terms of cosine and sine so that this is true. So we need to get 1 over here. So we're going to divide by 4/3 squared. And then we'll be able to get this. Okay. So we're going to have x squared over 4/3 plus y minus 2/3 over 4/3 squared equals 1. Oh, that's squared. Please check my math. If you think I made an algebra error, please, yeah.
What if the 4/3 cancel out because you have the coefficient of 4 over 3 x squared? Yeah, just be 1.
But this is squared.
Oh, okay, I see.
So when I divide by 4/3 squared, I get 1 more in the denominator. Is that
Yeah, that makes sense.
okay? Catch any other possible errors? Thank you for speaking up. Everything look good? All right, so look, so what we need is something squared plus something squared equals 1, and then we've got, then we can use cosine and sine, right? So whatever's inside there will be cosine, whatever's inside there could be sine. So we need something squared because we got the 1, now we need the whole thing squared, so it'd be what? X over 2 over radical 3 squared plus y minus 2/3 over 4/3 all squared equals 1. So now we can say we can let that what's inside the parentheses be cosine t, and what's inside the parentheses there be sine t, because cosine squared plus sine squared equals 1. Do you see? Does that make sense? So what will x be? X will equal 2 over radical 3 cosine t. If that whole thing is cosine t, then what is our x? X is 2 radical 3 times cosine t. And if this whole thing is sine t, then what's y? 4/3 sine t plus 2/3. We're very, very close. We got our x and y. We just need to see. Did that make a mistake? This whole thing equals sine t. Multiply by 4/3, and I think that's right. Are we good? So there's our x, there's our y, and what will our z be? 1 plus half of that. So, did I lose anybody? If I lost you, ask. Or if you think I made a mistake, ask. Yes, please.
So I just okay, right? For the z, you just plug in y back to the equation.
Yeah, because so now we have y, z is just 1 plus 1/2 of y. So z is just going to be 1 plus 1/2 of that. So I'm going to put it in and see if the curve comes out correct, okay? So what do we say? X was what? 2 over radical 3 cosine t. Oops. Great, okay, and then plus 2/3, 4/3 sine t plus 2/3, and I'm going to copy and paste that. 1 plus 1/2 of that. And turn this one off. That was the old one. Moment of truth. Here we go. Stop. All right, here we go. Moment of truth. Ha. Got it. All right, did you catch all that? So, because it's an ellipse projected in x and y, we know we're going to use something to do with cosine t for x, something to do with sine t for y. So we're going to eliminate z and get an equation of the ellipse in x and y. That was what all this was, and that was here. Here's the equation of the ellipse. And then we're going to set it up so that you get one thing squared plus one thing squared equals 1, and then that can be cosine inside, and that can be sine inside, and that allows us to get what x and y are. And then z just falls out from that second equation of the surface. Ask me if I lost you.
Why did you all of a sudden add the 2/3?
What's that? It's from this minus 2/3 right here. This whole thing equals sine t. Everything inside here is sine t.
Oh,
So you'd multiply and then you'd add. You see it? Yes? Is there a question? It's nice to see the curve appear correctly that we did all that math right? It's like a green bar, right? It's like a green bar. Okay. Other questions? All right, you guys try one then. Here we go. Nah. Where's the other one? There you go. That's easier. See if you can draw it though. So this is easier. The math is easier, but the sketch is dicey. So can you get the sketch of the surfaces and the intersection? But the math of getting the vector function is a little bit easier on this one. Okay, work together. Your teacher needs a break. Okay, these are both what? These are both what? Both of these are the same. We can use the same word for both of them. Cylinders, right? They're both cylinders. First one. Circular cylinder like this. Radius of 4. What's the other one? So it's a parabolic cylinder. So this is a parabola, say a parabola in the xz plane, but then y can extend, right? So we're going to extend in the y direction. So we're going to get something like this. So what will happen when those two intersect? Anyone know what that will be? So where's this going to hit first? It's going to come in and hit where? You see it's going to hit the bottom? And then as it moves through, the intersection is going to go like up, and the highest point is going to be here. And then back down there. And then same in the back. Let's leave this to the professionals. Blue better. there? No, not much. All right. Okay, so then what do we get here? So the intersection, oh, I didn't do that. So the intersection is this thing. Is it showing up? So it's like a it's like a big folded potato chip or something. The edge of it, right? The edge. Okay, so in the xy plane, it's what? So what is it in the xy plane? So if we look down the xy plane, we see just a circle. Okay, what about in the yz plane? What do we expect? Is it going to be a parabola? Maybe. We'll see. The math will tell us, right? The math, when we do the math, it will tell us if that's a parabola or not. And this looks similar. Okay, so did you get the function? Did you get the vector function for that yellow curve? How are we going to approach this one? So yeah, so it helps to draw the picture, certainly, and get a good image of it, but you could actually do the math without ever having the picture here and get the math right, okay? What are we going to do? Again, what's the projection in the xy plane? So, Trevor, what are we going to do? Projection in the xy plane is a circle.
Oh, you want me to do the cosine sine?
I want all of us to do the cosine sine.
Okay. I did it in the other form, but
No, so if you have a circle or an ellipse in one of the projections, you're going to use sine and cosine. That's what's called the natural parameterization. It's natural to do that. But if you do t, then you're going to have maybe some ugly inverse cosine and sine or square roots or something that's not as convenient. So whenever you've got a projection into one of the planes that's a circle or an ellipse, you need to know how to do it with cosine and sine. So this one's much easier than the last one.
would our x be 4 cosine of t?
Huh? What's
And our y would be 4
Yep.
sine of t?
Because we can do, right, x squared over 4 squared plus y squared over 4 squared equals 1, divide by 16. And then what is cosine t is going to be? X over 4, right? So we can just bring the square out. And so now cosine t is x over 4, which he said x is then 4 cosine t. And y is 4 sine t. So z is 1/2 4 cosine t squared. That's the parametric version of that yellow curve. So is it a parabola? Well, we'd have to put like y and z together, right? And then use some identities to see, like trig identities, to eliminate cosine or sine, to see if you actually get just like z is something y squared. We won't take the time to do that. But does that make sense? If you want to check to see if you actually have a parabola when you're looking at, say, the yz plane, then you'd have to combine those two equations, eliminate t, and that's going to take some trig identities to do that. And then if you end up getting a parabolic equation of y and z, then that confirms that yes, you're looking at a parabola when we look down the yz in the yz plane. We won't take the time to do that. Okay, so let's just look at what I write here. There it is. 4 cosine t, 4 sine t, is it 8? 8 cosine squared t. And this a is just making my intersection a little thicker here. I've got some different values of a. So just ignore the a. Okay, questions on this example? Okay, so got a little time left to start something new here. Remember, next topic. Remember this, we're talking about, when I introduced vector functions, I showed you this is my favorite one. And how does it work? For every value of t, you get a vector, right? Every value of t gives you a vector. That's what a vector function is. But if you put all those vectors that come out of the function in standard position and let t increase gradually, and then trace out the tips of those vectors, you get a curve. That's why we're saying that vector functions are curves. Because in essence, vector functions are a set of vectors. So to get the curve, you got to put all those vectors at standard position and let t increase, let t vary. And then the tips of those vectors are going to sweep out the curve. And so we saw that last time. Okay, now I'm going to show you a different vector. And I want you to, so is it showing up as blue on the screen? Let's make whatever observations you can about this blue vector. So what do you observe about the blue vector? What do you observe about the blue vector? Well, vectors have two qualities to them. What are the two qualities about vectors? Magnitude and direction. What do you want to talk about first? Direction. Direction. What's the direction of the blue vector? Which way is it pointing? It's pointing in the direction that the curve is being swept out at that moment, right? So it's always pointing in the direction of the curve. Okay? Everyone see that? So it's pointing exactly. So if this were a particle flying through space, it's the direction of the particle at any moment, right? It's the direction of the particle as it moves at any moment. Or the direction of the particle's movement, I should say. Okay? What about the magnitude? Is it constant or changing? Changing. Okay? So we see it's at the beginning. At the beginning here, it's large. We get to the loop and it's small. And then it gradually gets much larger again. So what do you observe about the magnitude of this vector? What's that?
I don't know, I'm looking at it like it's speed.
Like speed? Okay, so can we talk about like the variable t and the curve? So how does it relate to the variable t and the curve? So yeah, that's the idea. That's the idea. Magnitude of the change of what? With respect to what?
With respect to the curve.
The other way.
Or the curve with respect to
Right, so do you see that this is, the magnitude of that vector is showing how much of the curve is swept out with respect to how much t changes. So I'm showing t increasing constantly, right? So this is t increasing constantly with time. Okay, that's down there on the left. So do you see that when that blue vector is large, you're getting lots of the curve for a same change in t. But when the like on the loop, what's happening there? On the loop, you're getting less curve for the same change in t, so that vector is shorter. So if we put those two things together, the direction is the direction of the curve, and then the magnitude is how much curve you get for a change in t. What do you suppose this thing is? Yeah, so that should feel a lot like derivative, right? That has the two qualities of derivative. Like it's tangent, or the direction of the curve, and its magnitude would be kind of the rate in which the curve is being swept out with respect to t. So let's find that function. So that function is exactly what you'd hope it'd be. How do you think you find that? It's just the derivative component-wise, right? So it's like, okay, sometimes things work out just the way you want them to. Not always, but this is nice. So the x component is negative sine t. Y component is 4t cubed
minus 12t squared plus
plus 6t
6t.
and 2.5 cosine 5t. Did I do the math right? So this is the vector function's derivative. Vector function's derivative. And so this is likewise is a new vector function. It's a set of vectors itself. But it doesn't make sense to put these as standard position vectors, right? It makes a lot more conceptual sense, to put the tail of this vector always at the tip of its corresponding R vector, right? So in terms of conceptualizing how it relates to the curve, this is the way we want to think of the derivative as take that vector, all those vectors, and put their tails on the tip of the corresponding R vector for the same t, right? All right. One more. What's this? I got a red one now, a red vector. What do you see about this?
Magnitude's always the same.
Magnitude's always the same. What about the direction?
Still the direction.
It's the same direction as this one. It's the same direction as this one, but its magnitude is always the same. And so what do you suppose that is? Yeah, and it's so I can tell you that its magnitude is 1. So how would we get that vector function? What would we do? This is called the unit tangent vector. Unit tangent vector. How would we get that vector function? Divide by the magnitude of the vector function we had before. So it'd be r prime of t, what? Divided by the magnitude of r prime of t. So we're unitizing, just the way you unitized vectors before, but now you're doing it as a whole function, right? So that would give you still a new function, a quite ugly one, right? So each one of these would be divided by the magnitude of this, which would be the square root of that squared, plus that squared, plus that squared. So equals ugly. But important. But important. All right. Recitation tomorrow. Blood work Friday.